Hello everyone, my name is Wang. I'm pleased to present our research works in Eurosteel 2021. This paper, entitled In-Plane Seismic Performance of SC Wall to Foundation Connections, was accomplished in 2019 when I was still a PhD candidate in Tongji University. And now, as you see, I'm a post-PhD in Chongqing University. Quite long period. Okay, back to this paper. It is mainly about the experimental program since we just finished the test at that time. So I will introduce the content of this paper first and then give a short summary about further relevant works we have done. First part, background. Let me introduce the steel plate composite wall first. It is also called SC wall, which is mainly composed of two steel plates and infilled concrete. The steel plates at opposite sides are generally connected together, and a typical connecting method is using vertical stiffening angles and horizontal tight channels. Besides, the headed studs are welded at the internal face of the steel plates to ensure the composite action. As you could imagine, all the steel components could be saved, reducing the overall cost while enhancing the mechanical behavior, especially under seismic or impact conditions. These advantages promote the wider application of SC structures, such as in nuclear power plants, ocean structures, and high buildings. Definitely, the SC wall has to be reliably anchored to the RC foundation. Two typical types are introduced here. First one, lap splice connection, where the dowel rebars serve as the connectors between the SC wall and the RC foundation. And another one is embedding connection. That is, the SC walls itself extend into the RC foundation directly. Since the in-plane seismic behavior of the two types of connections have not been adequately studied, we perform the experimental investigation of them. Totally, 4 large-scale specimens were designed. The test parameters include the wall height and connection type. Also, the constant axial compression is applied. As for the fabrication, first, the SC modules were produced in factory. Then, all the steel components were installed, including SC modules, dowel rebars, shear lugs, rebars of RC foundations. Third, the formworks are ready. At last, casting concrete. The test is conducted in Tongji University. 2 hydraulic actuators were installed to apply the axial compression and the horizontal cyclic load respectively. The RC foundation is fixed on the ground. Here is the photo. During the test, the transverse cracking and crushing of concrete were observed in all the specimens, but the failure modes are different. For lap splice specimens, the yielding and local buckling of rebars indicate the fracture failure of connection. However, the fracture failure of SC wall itself is defined for embedding specimen because the steel plates yielded even teared after the cyclic loading, and buckling and local buckling also appeared. The force displacement skeleton curves are plotted, and the capacity and ductility are analyzed. Basically, the specimens with larger wall height has higher flexural capacity and ductility. Moreover, the lap splice connection has better ductility than the embedding one. After that, we predicted the capacities of test specimens by existing equations. As we did not find any equation for the strength of lap splice connection, we could only use the shear and flexural strength equations for SE wall proposed by Japanese code JEAG 4618 and COOT, etc., respectively. From the prediction results, we see that the peak load for the higher specimen is far less than predicted shear strength. It is reasonable since it did not fail by shear. However, for the lower specimen, although the ratio is less than 1, it is close to 1, which means the shear-flexure interaction should be noticed. Meanwhile, the equation has underestimated the flexural capacity of SE wall. The possible reason can be: first, the benefit effect of the small axial compression is not considered. Second, the strain hardening of steel materials is not considered. And the last one, the contribution of the vertical welded stiffening angles is not considered. Also, of course, the equations for the fractal capacity of lap splice connection should be proposed in the future. Last part, I will show the conclusions and our further works. In this paper, 4 large-scale SE wall-to-foundation connections were subject to combined axial compression and cyclic in-plane lateral force. The results show that lap splice connection and embedding connection are both feasible for practice use. As for the failure modes, the flexural failure was observed in all the specimens, but the failure on the connections was observed for lap splice connection, and for the embedding connections, the SE walls themselves failed. Besides, the existing equations for the in-plane shear and flexural strength of SE walls could not reasonably predict the load-carrying capacities of the test specimens. The ductility is also analyzed. The results show that the ductility of the lap splice connection was better than that of embedding connections, and with the increase in the aspect ratio of SE wall, the ductility of the specimens was enhanced correspondingly. The further investigation were recommended, and it's mainly about first the beneficial effects of stiffening ribs and small axial compression. Second, the design detail of the 2 connection types. Third, the load transfer mechanism and the capacity of the lap splice connection under various load combinations. And the last, the shear flexure interaction effect should be noticed. Later, we published a paper about the SE wall to foundation test program. Here, the out-of-plane condition is also included. The test results are presented and analyzed in detail. After that, we carried out a numerical study about the flexural capacity of angle-stiffened channel types SE wall under combined cyclic lateral force and axial compression, of course based on the former test results. And we defined the stiffener strength ratio to consider the contribution of the angle stiffener. This ratio is used to calculate an equivalent steel plate thickness. Then we proposed the equation for the flexural strength of SE wall. These equations consider the contribution of stiffeners and also the small axial compression. The prediction on the test and the numerical results is reasonable and safe. Also, we studied the seismic behavior of flex connections between SE wall and RC wall. The L joint in SC structures are also studied experimentally, numerically, and theoretically. The failure modes are analyzed in detail, and equations for the joint shear strengths are proposed. The L joint composed of SC wall and RC wall is also studied. Here presents a list of our written paper about SC structures, and of course, there still remains a lot to be continued. And that's all for the paper and our relevant works. And thanks for listening. If you have any questions or something to communicate, you can contact with my email. And thank you again. Bye bye.